Okay, so thank you very much for your kind introduction. I'm Daniel Doménech from BCMaterials and the University of the Basque Country, Spain. And today I'm going to share some results regarding my thesis with the results of cobalt platinum thin films, where we can tune the perpendicular magnetic anisotropy, fabricating samples beyond ultra-high vacuum conditions. Okay, so first I will introduce the concept of perpendicular magnetic anisotropy. That is basically moving the easy axis of a magnetic thin film from the normal direction, normal to the film, perpendicular to the film. And because of that, we can open the door for a lot of applications like high-density magnetic recording, lowering the power consumption in spintronics, and also opens the door to novel magnetic textures. Okay, so for obtaining perpendicular magnetic anisotropy, cobalt platinum systems has been widely studied for more than 30 years. And those are commonly pursued by using magnetron sputtering and a large stack repetition number. Okay, so in our group, we decided to ask for a different question that was to obtain also PMA, perpendicular magnetic anisotropy, in cobalt platinum multilayers, but with the combination of three different conditions. All of them at the same time. That was obtaining by using electron-beam evaporation technique, using very low number of repetitions of the cobalt platinum stack, and also fabricating those samples under lower demanding pressure conditions. So I will explain very fast why we selected these three conditions, starting with electron-beam evaporation. There are two main mechanisms to fabricate those samples. Those are magnetron sputtering, that has been more widely studied, and also electron-beam evaporation. But the reason to stay with electron-beam evaporation is due to the geometry deposition, that is a non-conformal one, since the evaporated atoms, the incident atoms to the substrate, to the sample, will come in a very unidirectional direction compared to the conformal geometry from the magnetron sputtering geometry. So we are interested in having nano patterns coming from nanolithography. So we are interested that the edges of the nanostructures will be well defined. So that's the reason to use electron-beam evaporation. Another reason to use a low number of repetition of the cobalt platinum stack is to study for interfacial interactions coming from external layers in contact with the ferromagnetic stat, such as spin transfer torques, spin orbit torques, or exchange bias. And all of three interfacial interactions are always, its strength, its effective field, always is inversely proportional to the inverse of the total thickness of the ferromagnetic material. So in order to enhance those interfacial effects, we are interested in reducing the amount of layer repetition of the ferromagnetic stack. And finally, maybe this is the most unexplored condition of all of three, is to move the fabrication conditions, the pressure conditions during deposition, from ultra-high vacuum conditions to high vacuum conditions. Because historically, since the very beginning of the studies with cobalt and platinum systems, it is well known that only the 1-1-1 crystallographic ordering is the responsible, the main actor into promoting the PMA in those systems compared to other crystallographic orderings. So historically, all the groups worked in the 10 to the minus 8 up to 10 to the minus 10 base pressures in order to get high quality thin films and interfaces to promote this particular growth condition. So in our group, we decided to push these boundaries forward and try to obtain cobalt platinum systems fabricated under base pressures of 10 to the minus 6 millibar. That is deep inside in the high vacuum range and not ultra high vacuum range. And if PMA is obtained with these conditions, it will open the door to more accessible studies on cobalt platinum systems and other systems for obtaining high quality perpendicular magnetic anisotropy. So our goal is to obtain perpendicular magnetic anisotropy with the combination of these three conditions. And the approach will be to deposit different layer combinations of materials and thicknesses, comparing samples made at the same deposition run, thanks to a precise thickness control inside our electron beam evaporation, thanks to a microquartz balance. So For the results I'm going to present you next, we will maintain the cobalt thickness fixed only to 6 angstroms, and we are going to change to vary the thickness of the non-magnetic layers. Okay, so let's move to the results. Let's see if we can obtain perpendicular magnetic anisotropy under these rough vacuum conditions, starting with samples containing only platinum and cobalt. Okay, so results measured by polar mode microscopy showed that no matter the combination of cobalt and platinum thicknesses and orderings, no perpendicular magnetic was found at all in this configuration, since all the hysteresis loops resemble more like an hard axis behavior compared to the desired easy axis one. So we needed to go for another approach, that was to deposit a copper buffer layer below the ferromagnetic structure. And for samples containing at least 10 nanometers thick, now the hysteresis loop in the out-of-plane direction, now it is an easy axis behavior with a square loop and the remanence of exactly 1. Okay, so a copper buffer layer is mandatory for the emergence of PMA under these conditions. And furthermore, if we increase the content of copper, we can tune the coercivity in a very linear trend. And that was proven reproducible comparing several sets using the same deposition scheme. So we are very happy about these results, but now the question is how copper is improving perpendicular magnetic anisotropy, and the answer comes from structural terms. If we look at the X-ray diffraction patterns of this set, we see that for the cobalt platinum 111 crystallographic ordering, by maintaining fixed the amount of material, of the magnetic material, but increasing the amount of copper, we do see that for this particular peak, there is an enhanced 111 crystallographic ordering. So that is promoting the desired PMA. Okay, so we also measure that copper leads to larger cobalt platinum grain sizes, which correlates with larger surface roundness measured by atomic force microscopy, which strongly correlates with the increase of coercivity as a function of the copper layer thickness. So these are the main two mechanisms of copper improving and tailoring the perpendicular magnetic anisotropy in these rough conditions. So now we understand the role of copper. We have room to optimize parameters, and now I'm going to present another set of samples which only varies with the amount of platinum above and below the cobalt layer. Again, we are going to compare the same thicknesses of copper. And the results show that there are significant differences between the magnetic behavior for the same amount of copper by reducing the amount of platinum. As you can see, the coercivity are way higher than the previous set. So here we see that reducing platinum changes a lot the magnetic behavior. We also found that there is a critical value of the copper thickness below 6 nanometers in order to promote the desired PMA. So now the question is to also notice the role of platinum, since there have been a lot of magnetic change by changing this content of platinum. And for this question, we are going to fabricate another set only changing the amount of platinum by fixing the amount of copper on the set. And the results show that the coercivity of the samples decrease significantly as we increase the content of platinum. But what is even more important is for large amounts of platinum, the out-of-plane remanence, I mean the degree of perpendicular magnetic anisotropy, almost drops to 0 for large amounts of platinum. So PMA is lost for large deposition of platinum. And the reason also comes from structural terms, since for large amounts of platinum, there is an undesired crystallographic phase, the 2001, which is well known to be detrimental for the emergence of perpendicular magnetic anisotropy. So by this tiny amount of the undecided phase is enough to completely lose the perpendicular magnetic anisotropy effects on our samples. Okay, so now we understand the role of platinum and copper. We need to address a specific issue regarding for large amounts of copper due to its large copper optical absorption. We get magnetoptical noisy loops. And when we measure in the magnetoptical Kerr effect magnetometry, we see a very noisy loops coming from this loss of of optical properties. So in order to address this issue, we transition from only one repetition of cobalt to 2 repetitions of the cobalt platinum stack. And the results were very positive, since we can reproduce almost the same large coercivities, but this time reducing significantly the noise of the magneto-optical curve loops. Okay? So if we summarize all the different sets that we have compared to obtain a precise and high quality perpendicular magnetic anisotropy, we can see that we can tune the coercivity from 30 Ersted up to more than 450 Ersted by changing different parameters that are very reproducible. Okay, so finally, I will show you the applicability on nanostructures from this fabrication route. We have proven this fabrication route using electron-beam evaporation on nanostripes made by interference lithography. And as you can see, we can see a strong domain contrast between the up and down perpendicular states in curved microscopy. So this application route has been proved successfully. So to conclude my talk, we emphasize that we have obtained a strong perpendicular magnetic anisotropy under the combination of electron beam evaporation, a low number of cobalt platinum repetitions, and most importantly, deep inside the not ultra high vacuum conditions, but high vacuum conditions, 10 to the minus 6 millibar, thanks to the addition of a copper buffer layer. We have also proved that it is possible to tune its coercivity. We can enhance the magneto-optical curve signal by promoting to 2 cobalt platinum repetitions, and we proved its applicability on nanostructures. So that's my talk. Thank you very much for your attention.
Thank you, Danny. So now we are open for the questions. So Danny, these are polycrystalline films that you made, right?
Yeah.
Okay. So but if someone, like, it's a very stupid question, but if someone wants to make these ferromagnetic structures using sputtering and you use E-beam evaporator, which method would be you prefer? I know for the anti-ferro, people generally use this E-beam, not the sputtering one generally. But for the ferromagnets, what are your thoughts on this? Which would be good?
I'm not understanding the question. Sorry, can you repeat the question, please?
So these sort of fabrications, which method would you prefer? E-beam evaporation techniques or sputtering, or which is?
I mean, if we use magnetron sputtering, we can have a precise control of the thickness and also the degree of diffusion between layers. But the problem is, since we are interested in to get into nanostructures, we prefer electron beam evaporation due to its geometry deposition. But if we want to work with thin films, maybe we should work with magnetron sputtering.
Okay. So we have a question from Sonia. How does PMA vary on the wavelength of nanostrips? And in continuation, she is asking, and can we induce the PMA if we use ripples using ion beam irradiation on silicon substrates?
I'm not able to see the chat, so can you repeat the question again, please?
Yeah. So the first part of the question is, how does PMA vary on the wavelength of nanostrips?
That's okay. That's an interesting question. We didn't study it yet, but it is a to-do is in our to-do list. So yeah, we are going to study different widths of the nanostripes, and we are going to study the perpendicular magnetic anisotropy on nanostructures, transitioning from thin films to nanostructures. Yeah.
And she's asking, can we induce the PMA if we use ripples using ion beam irradiation on silicon substrates?
I'm not sure about it. We are trying to reduce the complexity of deposition using the most cost-effective systems. So we are trying to use the least amount of systems. So we didn't try this kind of approach. So I'm not sure about the results of that approach.
Okay. So we can have one more question, or otherwise I'll move forward. Any questions? Okay. Thank you, Danny, for the wonderful talk.
Thank you.
So, yeah.